This lecture is about catalyst deactivation. Although catalysts do not get consumed in a reaction, they lose their activity over time. And in this topic, we will analyze and understand how catalysts become deactivated and how you can regenerate them. At the end of this session, you will understand what the different types of catalyst deactivation are and how they can be modeled. You will also know how to analyze the regeneration of catalyst pellets that have been deactivated by coking. This uses what is known as the shrinking core model. Finally, you will know how to analyze dissolution of solids and understand the regions where the process is reaction limited and mass transfer limited. In topic 2, we assumed that the total number of active sites remained fixed. For the Langmuir-Hinshelwood mechanism, we derived the following expression, where K star is the product of the forward rate of surface reaction, KFR, the square of the concentration of sites, CT, and the adsorption equilibrium constants, kPa and kPb. We assumed that CT, the concentration of all sites, was constant, meaning it does not change with time. In other words, we assume that the catalyst activity remains constant throughout the catalyst's life. However, over time, real catalysts lose their activity due to a number of different processes. They can get damaged by attrition. Deposits can adhere to them and block pores and active sites, and they can be poisoned with other chemical species. These all reduce the activity of the catalyst. So the longer a catalyst is used, it goes from being fresh catalyst with a high activity to a spent catalyst with a low activity, or completely deactivated. Here, you can see the catalyst is becoming degraded over time, and the effect is both physical and chemical. You can see a definite change in color, and they may also become more brittle or fragile. They can become smaller too, due to attrition if you have high motion inside your reactor. Here, you can see that the size of the spent catalyst is smaller. So catalyst deactivation is defined as the loss of catalytic activity with time, and it is one of the major problems related to the operation of heterogeneous catalytic reactors. This diagram shows one type of catalyst deactivation. We have a monolith undergoing what is known as coking. It is a process by which carbon atoms are deposited in the pores and on the active sites of the catalyst. You can see that catalyst deactivation can also be a physical process. The structure of the monolith is degrading, probably due to prolonged exposure to high temperatures. So both chemical and physical deactivation can take place simultaneously with the main chemical reaction. Deactivation generally cannot be avoided. It will happen eventually. However, steps can be taken to slow down the process and avoid some of the consequences of deactivation. In the end, though, catalysts will need to be regenerated or replaced. In order to understand the processes of catalyst deactivation, we need to look at the mechanisms by which this can occur. As I said earlier, this can either by chemical or physical mechanisms, which are typically divided into four main types. Coking or fouling is where material, usually carbon, depicted by the black regions here, is deposited on the internal surfaces of the pores and covers the active sites, the crystals of metallic catalyst. If active sites are covered by coke, then that makes them unreachable by the reactants. Sometimes pores can become completely blocked, as you can see here, where a pore channel is completely blocked. This significantly reduces the surface area available for catalysis. The active sites in the blocked pore channels are inaccessible. Coking is essentially a physical form of deactivation. A chemical form of deactivation is poisoning. Here, the active sites on the catalyst crystals can also bond with inert or unwanted chemical species. Here, we can see an enlarged view of the surface of the metal crystal. The oxygen atom and the carbon monoxide are the reactants. The sulfur atom is the poison. If sulfur atoms adsorb onto the sites more strongly than the reactants, then they preferentially take up sites, leaving fewer available sites for the desired chemical reaction. The third type is sintering or agglomeration. What do you think is happening here? Sintering is the process of compacting and forming a solid mass of material by heat or pressure without melting it. In catalysts, active sites can agglomerate due to compaction or migration due to high temperature. It is easy to understand the effect of higher pressure. Higher pressure means more compaction. On the other hand, if you have high temperature, atoms are more active, meaning they vibrate more, so more chances for migration. So here, we can see that smaller crystals of catalyst join together to form larger ones. What do you think happens to the total surface area? The total surface area reduces, so there are fewer active sites available to catalyze the reaction. The last main type of deactivation is solid phase transformation. What do you think is happening in this type of deactivation? Here, the catalyst support material, depicted by the brown regions, changes its physical configuration. The structure can weaken and deform, causing pores to collapse, like here, and the pores become blocked. Obviously, this reduces the number of active sites available. Other mechanisms involve loss of catalyst atoms due to volatilization. Here, catalyst atoms leave the metal crystal and become part of the gas phase or the liquid phase. Catalyst pellets can also be damaged by erosion and attrition. So this is the wearing down of the catalyst. For example, in a fluidized bed reactor, due to collisions with other catalyst pellets, the walls of the reactor, and so on. Let's look at coking in more detail. Coking or fouling typically occurs in catalytic reactions involving hydrocarbons, where side reactions produce carbonaceous residues, usually called coke or carbon, that are deposited on the surfaces of the pores, covering the catalyst's active sites and eventually blocking the pores completely. There is a distinction between coke and carbon. Do you know what that is? Although we often use the terms interchangeably, strictly, carbon refers to atomic carbon, which comes from the disproportionation reaction of carbon monoxide, whereas coke refers to the deposits produced from cracking or condensation of hydrocarbons. So carbon is just carbon, but coke is mostly carbon with some other atoms such as hydrogen, oxygen, nitrogen, and sulfur. This picture shows the effect of coking on nickel catalyst after the reforming of dodecane. The fresh catalyst is on the left and the deactivated one is on the right. Here, the carbon deposits are increasing from left to right. Now, let's look at poisoning in detail. Poisoning can happen when your feed streams contain impurities that can adsorb onto the active sites of the catalyst. This is strong chemisorption. The poison occupies the active sites, which prevent them from catalyzing the desired reactions, so you have loss of activity. Different catalysts have different poisons, as you can see from this table. These are the processes and the corresponding catalysts and their poisons. Here, catalytic converters in cars. The catalysts are platinum or palladium, and they are poisoned by lead, phosphorus, and zinc. So lead is not just toxic to humans, it also poisons the catalytic converter. That's why we have unleaded petrol. Steam reforming and methanol synthesis are topical nowadays due to interests in the hydrogen economy and the methanol economy. The idea is hydrogen and methanol are cleaner replacements for fossil fuels to power transport and also to produce electricity and heat. Here we have two different processes using the same catalyst, and here they have different poisons depending on the process. Finally, there are many processes that use transition metal oxides as catalyst, and they are poisoned by lead, mercury, arsenic, and zinc. Poisoning can be classified in a number of ways. First, poisons can be either non-selective or selective. For non-selective poisons, the catalyst active sites have an equal affinity for the poison. This means that the poison has an equal probability of adsorbing onto any of the active sites, and so the activity of the catalyst reduces linearly with the amount of poison adsorbed. For selective poisoning, the characteristics of the active sites are not all the same across the surface. Some have stronger activities than others. So the strongest active site will be poisoned first. This means that the activity of the catalyst has a nonlinear relationship to the amount of poison adsorbed. Another classification of poisoning is whether it is reversible or irreversible. Poisoning may be reversible if the poison does not adsorb too strongly to the active sites. Simply removing the poison from the feed or passing some inert gas through the catalyst bed may be enough to remove the poison from the catalyst. One example of reversible poisoning occurs in fuel cells. Hydrogen is one of the fuels that can be used in fuel cells to produce electricity. If you produce the hydrogen from hydrocarbons, then there can be some contaminants in the hydrogen, such as hydrogen sulfide. This hydrogen sulfide can then preferentially adsorb onto the nickel catalyst surface, preventing the hydrogen from getting to the surface. Here you can see that the cell voltage drops suddenly due to poisoning when hydrogen sulfide is present in the feed. However, as soon as the hydrogen sulfide is removed from the feed, then the adsorbed hydrogen sulfide comes off. There is an equilibrium between the hydrogen sulfide in the gas phase and the hydrogen sulfide on the surface of the catalyst. And if you remove the hydrogen sulfide from the feed, then there will be less hydrogen sulfide in the gas phase. And as a result, the adsorbed hydrogen sulfide on the surface of the catalyst can come off. By just removing the hydrogen sulfide from the feed, you can see here the voltage increases again almost instantaneously. Again, when hydrogen sulfide is present in the feed, the voltage drops. So the catalyst has become less active, so fewer hydrogen reactions are taking place. And then as soon as the hydrogen sulfide is removed from the feed, the cell voltage returns to normal. In this case, it is enough to just remove the impurity from the feed. But in other cases, you may have to stop operation and flush the adsorbed poisons out with an inert gas. If the poison is adsorbed too strongly, then it is very difficult to remove it from the catalyst, and the catalyst may be permanently damaged. We have to be very careful in this case to make sure that there is no poison in the feed, because catalysts are expensive and we do not want to replace them frequently. In sintering, active surface is lost because the active sites agglomerate. Here you have structural modification that is generally thermally activated. High temperature means that the metal atoms can vibrate more, and then they can come together and form larger crystals. High pressure can also induce compaction, also resulting in larger crystals. For example, this can typically happen when you have precious metals on an inert support material. The agglomeration of the small metal crystals can be provoked by high temperature and high pressure, forming larger crystals with lower surface area to volume ratios. This is not good because we want high surface area to volume ratios. This is a tunneling electron microscopy image of two cobalt particles coalescing on a catalyst support surface. Here we can see two small cobalt particles, and when they combine, they may look like this big one here. If you want to find out more about catalyst deactivation, then this review article is a good one to read. We will define catalyst activity as they did in their paper. Catalyst activity, A of T, is defined mathematically as the rate of reaction at some time t divided by the rate of reaction at some initial time t equal to 0. The time t used in the numerator is the time that the catalyst has been in use, or we can say that this is the rate with the degraded catalyst at time t. Here in the denominator, we're looking at the rate at time equal to 0. This is the time when the catalyst is fresh. In this graph from the paper, catalyst activity has been measured for various catalysts as they are poisoned with hydrogen sulfide. Here we have cobalt, ruthenium, iron, and nickel. And you can see that less than 0.1 parts per million of hydrogen sulfide. Note that the units on the x-axis is parts per billion. With that very small amount, zero point 0.1 parts per million, can reduce the activity to less than 0.1%. Even a few parts per billion can cause a loss of activity of between 90% and 99%. Since the activity of a catalyst, and hence the rate of reaction, is related to the number of active sites on the surface, the catalyst deactivation can be considered as the decrease of the number of active sites on the surface. Another way of defining activity is by taking the ratio of the number of active sites on the surface at time t. So that's n subscript t to the number of active sites when the catalyst is fresh. So n subscript 0. So we denote this as alpha, which is related to the activity we defined in the previous slide in terms of the rates, since the rate is related to the number of active sites on the surface. Again, we can look at catalyst deactivation as the decrease in number of active sites on the surface, which also means a decrease in the rate. Although alpha and A of t are related, it is difficult to find a mathematical expression relating them because the reaction rate that we can measure is limited by all of the steps in the catalytic process. So for example, including external diffusion or internal diffusion. Therefore, the overall rate, negative RA, may not be directly proportional to the number of active sites and subscript T. Remember that the number of active sites affect the rate of the surface reaction only. Even if the overall rate is surface reaction limited, there are some deactivation processes such as selective poisoning that we talked about earlier that do not result in a linear decrease in activity as more poison is adsorbed onto the catalyst. Therefore, alpha and A of t are not guaranteed to be the same. The point here is that when you say activity, you should always say what it is based on. Is it based on the observed rates or on the number of active sites? As we have seen, catalyst deactivation is a dynamic process. The activity decreases with the amount of time the catalyst has been in use. There are two general ways to describe the deactivation kinetics. They are called separable and non-separable kinetics. Separable kinetics is when you can describe the rate of reaction as the product of two functions. The rate when the catalyst is fresh, so that's Ra prime, bracket fresh, multiplied by some function of time or the conditions of the catalyst. So A bracket past history. You learned how to write Ra prime fresh catalyst from the previous lectures. And we defined A of t, so the catalyst activity, in the previous slide. And this depends on how you started the reaction. It may also depend on the concentration of reactants. We will discuss an example shortly. Non-separable kinetics is more complicated, and you cannot separate the rate into a product of the reaction rate with a fresh catalyst and another function of time. The rate is a more complex function of the past history of the catalyst and what a fresh catalyst would do, where you cannot separate them out into two functions. Let's look at an example of separable kinetics. The dehydrogenation of methyl cyclohexane, denoted by A, to toluene, represented by B, proceeds according to the following mechanism. A adsorbs onto the catalyst surface to form AS, with rate constants K1 for the forward reaction and K-1 for the reverse reaction. AS, the adsorbed methyl cyclohexane, then reversibly reacts to give BS, the adsorbed toluene. Hydrogen is also formed, but it is not shown here for simplicity. The rate constants for the reaction where AS goes to BS are K2 and K-2. Finally, BS desorbs from the catalyst to give B and return a free active site S. And the rate constants are K3 and K-3. In addition, AS can form coke, denoted by C. For example, the reactant bound to an active site, so that's AS, can decompose into molecules that are deposited on the active sites or pore channels and make the active sites inaccessible to the reactant, methyl cyclohexane. We will assume that the step from AS to BS is the slowest step or the rate determining step, and that it is essentially irreversible. That means that K negative 2 is significantly smaller than K2. So the reaction from AS to BS is irreversible. And K2 is less than K1, K negative 1, K3, and K negative 3, which essentially means that the reaction from AS to BS is the slowest. We will also assume that, as in most situations, the rate of coking is small compared with the rate of reaction. So K4 is less than K2. So the main reaction is faster than the coking reaction. Also, coking is usually not easily reversed. So K negative 4 is significantly smaller than K4. So overall, this means that most of the AS goes to BS and only a small proportion goes to C. BS very quickly goes to B plus S, with very little going back to AS. Once C is formed, very little goes back to AS. Essentially, the coke is permanently blocking the site S. Our aim is to write the overall rate expression for this mechanism. And we know that the overall rate is equal to the rate of the limiting step. The step where AS goes to BS is the limiting step. So we will need to write a rate expression for this step. So that is negative RA double prime. This is equal to the rate of the forward step. So we have K2, the rate constant for the forward step, times the concentration of AS, minus the rate of the reverse step. So we have K negative 2 times the concentration of BS. So earlier, we assumed that this step is irreversible. We said that K2 is significantly higher than K negative 2. So we can write negative RA double prime as K2 times CAS. We need to express the surface concentration in terms of the bulk concentrations. And we can use the concepts that we learned from topic 2 to do that. So we can use the formula for the competitive Langmuir isotherm. We can write CAS over CT. This is equal to KA CA divided by 1 plus KA CA plus KB CB. So note that we are writing this expression in terms of the bulk concentrations of A and B. Okay, because we have methyl cyclohexane for A and toluene for B, and most likely they will be in the liquid phase. But if we were given the temperature and pressure, we need to check. And if we find out that A and B are in the gas phase, then we should express this in terms of the partial pressure. Okay, so but here we're writing this in terms of the concentrations. So also note that the denominator of this includes all of the species that are competing for the active sites. Ones that are competing for S. Okay, and they are A and B. So what about C? So C is the coke. So note that C is not chemisorbed. So that's why it is not in the denominator of the Langmuir isotherm. Okay, but C is deposited on the surface of our catalyst, and it blocks the active sites. Okay, so we will capture that later when we looked at CT. So this affects, so the coke affects CT. So as more coke is formed, CT decreases. So going back to our rate, we can now write this in terms of the bulk concentrations using this expression. So we have negative RA double prime, and this is equal to K2 times CAS, and CAS is KA CA CT divided by 1 plus KA CA plus KB CB. Okay, so we are not done yet. So we need to express CT as a function of time. And also CT depends on the concentration of A and B. Okay, so because now we have catalyst deactivation. So we have some coke formed and CT is no longer constant with time. So we need to find that function. Okay, so CT is now a function of time, CA and CB. But notes that CA and CB are also functions of time. So how do we do that? So we need to write the rate of formation of C. Okay, so we can use this. So this is the step for the formation of C. So we can write RC double prime. This is the rate of formation of the coke C. And earlier, we assumed that this step is irreversible. We said that K4 is significantly higher than K negative 4. So we can write this as K4. So this is the rate constant of the forward steps times the concentration of AS. But we have an expression for CAS in terms of the bulk concentrations. So this one is K4 times Ka Ca Ct divided by 1 plus Ka Ca plus Kb Cb. So now for every mole of C formed, 1 mole of sites are permanently blocked. So that means that Ct, which is the total number of sites, either free, so that's S, occupied by A, As, or occupied by B, Bs, decreases as C is formed. Okay, so the rate of change of the concentration of total sites is equal to the minus the rate of change in the concentration of coke. We can write that mathematically. The rate of change in the concentration of coke, this is equal to the negative of the rate of change in the concentration of the total number of sites. We have this relationship. And this can be related to the rate of formation of coke. So we have to make the units consistent. So the units of this is mole per second per square meters of the catalyst surface, while the units of each of these terms are, this is mole per second per m cube. Okay, so we need to multiply this by the specific surface area of the catalyst with units m squared divided by kilogram catalyst. And then we need to multiply this by the catalyst density. So the units of this is kilogram catalyst per cubic meter of catalyst pellet. So the units of this whole term is mole per second per m cube, which is consistent to the units of these terms. So now we can write negative dCt dt. This is equal to rho c SA times RC double prime. Okay, so rate of formation of C, and that is equal to this. Okay, so we can rearrange this. We can write dCt over Ct. So from the right-hand side, this is equal to negative from the left-hand side, and we have rho CSA K4 KA CA 1 plus KA CA plus KB CB. And then we have the dt here. And we can integrate. Limits of integration, this is at time equal to 0 to time t. And at time equal to 0, the total number of sites is Ct0. And at any time t, we have Ct for the total number of sites. So evaluating the integral, so for the left-hand side, we'll have log of Ct over Ct naught. So I have already substituted the limits of integration. And for the left-hand side, okay, so we can't integrate it with respect to time because Ca and Cb are functions of time. Okay, so we can just leave this whole term inside the integral. So this is equal to 0 to time t. So we have a negative sign. We have rho C S A K4 Ka Ca over 1 plus Ka Ca plus Kb Cb dt. So this will give us the expression that we're looking for. We're looking for Ct as a function of time and concentrations of A and B. Okay, so solving for Ct, we'll have Ct0 times the exponential of this whole term here. So we have negative 0, integral from 0 to t, rho CSA K4 Ka Ca 1 plus Ka Ca plus Kb Cb dt. So we can now substitute this Ct into our rate expression here. Okay, so doing that, we'll have negative Ra double prime. So this is equal to K2 Ka Ca. Okay, and then we have Ct. I'll write down the denominator first. So we have 1 plus Ka Ca plus Kb Cb. And then Ct is equal to Ct0. And we have this exponential decaying function. Negative the integral from 0 to t of rho CSA K4 Ka Ca 1 plus Ka Ca plus Kb Cb dt. So you can see that this term here, so this is the same as the rate at time equal to 0 when the catalyst is fresh. Okay, so we can write this. So this whole term here, this is equal to negative Ra double prime at time equal to 0. Okay, so when the catalyst is fresh. So the second term here, this exponentially decaying function, is just some function of time. Okay, so we can write this as A of t. So we have separated our kinetics out into the rate with fresh catalyst multiplied by some function of time. This function takes into account the history of the concentrations of A and B because it is an integral up to the current time t. We can do the same with a simpler case where the catalyst deactivation does not depend on the concentration of the reacting species. Let's say the coking reaction rate is just a function of the total site concentration. We can write the rate of change in the concentration of the coke is equal to the negative of the rate of change in the concentration of the total sites. And this is equal to some constants K1 times Ct. Again here, the catalyst deactivation does not depend on the concentrations of the reacting species. It only depends on the concentration of the total sites. So we can rearrange this dCt over Ct equal to negative K1 dt. And we can easily integrate this from time equal to 0 to time t. And here we have Ct0 and here Ct. So evaluating the integral, we'll have the log Ct over Ct0. This is equal to negative K1 t. And we can solve for Ct. Ct is equal to Ct0 times exponential negative K1 t. So we can substitute the expression for Ct into our rate expression. So we can write negative Ra double prime. This is equal to K2 Ka Ca 1 plus Ka Ca plus Kb Cb times Ct. Ct is this Ct0 times exponential negative K1 t. So again, this term here is our rate at time equal to 0 when the catalyst is fresh. And this term here is some function of time. So again, we have expressed our rates. Okay, so this is at any time t into the rate when the catalyst is fresh times a function of time. The next two slides show what we did on paper and the expressions that we derived. Other methods have been developed to describe coke formation. Some empirical ones are shown here. Voorhees proposed a power law expression for the formation of coke. The concentration of coke, Cc, is equal to a constant A times time t raised to n, where n is a number around 0.5. The power law is a reasonable approximation because as time increases, the rate of formation of C reduces because n is less than 1. This is to be expected because the total number of active sites reduces as more coke is formed over time. Monk and Bischoff introduced an empirical factor into the expression we derived for the rate of formation of C. This is very similar to the Rc double prime we wrote earlier, but there is an extra factor, phi c, which can be determined experimentally. Power law expressions have also been used to model the sintering of metal catalysts on a support medium. Here, D is the metal dispersion. This is the number of exposed metal atoms, in other words, active sites, as a fraction of the total number of metal atoms in a unit mass of catalyst. It determines a catalyst's properties such as its activity. D naught is the metal dispersion at time equal to 0 before any sintering has taken place. So the rate of change of the dispersion relative to the initial dispersion is proportional to the ratio of the dispersion at any time t to the initial dispersion raised to an empirical constant n. N can be determined experimentally. This is a good place to stop so that you can have a break. In part 2 of this topic, we will talk about catalyst regeneration.